and hi everyone, I am Dr. Chuan Kitian from 111. Today I would like to discuss about extremum problem. That we start with critical point. Critical point is the point in the domain of the function where the function is either not differentiated or derivative is equal to 0. Stationary point. Stationary point is a point on the curve where the gradient is 0 and the tangent of the curve is horizontal. It can be a maximum stationary point or a minimum stationary point. For a stationary point, f prime x equals to 0. Finding stationary point. For example, find the coordinate and nature of the stationary point of the function fx equals to x squared minus 6x minus 7. Solution. The first step, you must differentiate the function to find the value of f prime x. So you will get the value of f prime x equals to 2x minus 6. The next step, put f prime x equal to 0 and solve this equation to find the value of x. So you will get the value of x equal to 3. The next step, substitute this value into original function to find the value of y. When x equals to 3, y equals to 3 square minus 6 times 3 minus 7 equals to negative 16. So you will get the coordinate of the stationary point are 3, negative 16. The last step, examine the gradient on either side of the stationary point to find its nature. When x equals to 2, f prime 2 is negative, so the tangent is going down. When x equals to 3, f prime 3 is 0, so the tangent is straight line. When x equals to 4, f prime 4 is positive, so the shape of the tangent is increased. This shows a minimum point. Thank you.
Next, we're going to go through an example. So first of all, we're going to see and identify the keywords from this question. So what are the first keyword we can get? It's a cylindrical can. They say a cylindrical can is to have a volume, you have to highlight volume, of 250 pi cm3. Since the question says it's volume, so I'm going to label it with a letter V. Next, they say find the dimension of the can, which is made of least amount of material. What can we identify from the word dimension? Dimension here actually indicates the area, so I label it with an A. And least over here actually indicates that it's actually minimum. That's why they say they use the word least. It's minimum. So come, let's look at the steps in solving this question. So first we need to draw a label diagram. As you can see, I've drawn a cylinder here with a labeled height h and also a labeled radius r. Next, I'm going to form the equation and express the quantity that we want to optimize as the subject of formula with one variable only. Always keep in mind one variable only. So let's look at equation 1 here. Given the volume of the cylinder is 250 pi, so my first equation for volume would be V equals to pi r square h. So pi r square h is actually the volume, right? So it's 250 pi. So since I have two variables here, r and h, I'm going to eliminate my h, or I can say I'm going to make my h as a subject and I'm going to find it in terms of r. So in order for me to find h in terms of r, I'm going to divide 250 pi with pi r square. And as you can see, the pi and pi I can cut, so I'll get 250 over r square. So this is my h in terms of r. So next, let's look at equation 2. So equation 2, let A equals to the amount of surface area. Actually, it's the total surface area. So A equals 2 pi r square plus 2 pi r h. This is my equation at first. So you can see I'm just going to substitute the h, the value of h I obtained here in terms of r into here. So I'll get 2 pi r square plus 2 pi r bracket 250 over r square. So you can see I can cut this r and r here. So I can obtain 2 pi r square plus 500 pi over r. So this will be my final equation for total surface area. Let's look at third thing that we need to do, finding the first derivative, setting the derivative to 0, and also solving. So the first derivative here actually is dA over dr. So my dA over dr will be 4 pi r minus with 500r over r squared. This is my first derivative. Next, I'm going to find dA over dr. I'm going to equate it to 0 in order for me to find my value of r. So 4 pi r minus 500r over r squared equals to 0. Then I'm going to equate my denominator to get a single equation like this. So 4 pi r cubed minus 500 pi equals to 0. And then I'm going to make my r cubed as the subject. So r cubed will be 500 pi over 4 pi. Next, r cubed equals to 125. The pi and pi can cut. And then the cube root of 125 will give you a positive value of 5 cm, which indicates the radius of the cylindrical can. So now we already find our value of r. Always remember, r will always be positive because it's a length. So next, what I'm going to do is confirmatory tests of minimum, because the question says least, right? So that's why I'm using minimum by using second derivative. What is the second derivative here? Is actually the d square a over dr square, which is 4 pi. I'm going to differentiate my first derivative again. So to get 4 pi plus 1000 pi over r cubed. So when I differentiate, I get this equation. So now I'm going to substitute the value of r equals to 5, just now I obtained, into this derivative. So hence I will obtain d square a over dr square equals to 4 pi plus 1000 pi over r cubed. Just now I replaced with 5 cubed. So I will get a value of 12 pi. Since it's a positive value, so it indicates that it is minimum. This one is very important, it's minimum. So since d square a over dr square is greater than 0, it's a positive value. So therefore, we can make a conclusion that the area of the cylindrical can is minimum when r equals to 5. This is our small conclusion first. So next, we're going to see conclusion for the final answer. For the overall question, the conclusion will be when r equals to 5 cm, we can actually find the value of h, right? Just now we got the equation h equals to 250 over r squared. So I'm just going to substitute my r with 5, you can see here. So 250 over 5 squared, you'll get 250 over 25. So then you'll get a value of 10 centimeter, which is the height of the cylindrical can. So now we need to make a final conclusion for this question. This one is very important, so I'll just mark it with a star, indicates that it's very important. So the least amount of material is achieved if the radius, which is the r, of the cylindrical can is 5 cm and the height is 10 cm. Therefore, we have done this question completely. That is how we get to know that differentiation can actually be used in our daily life. That's all from me. Thank you very much.
Now we are going to look at problems on rate of change on distances between two cars. Two cars A and B start at the same location. Car A leaves at 8 a.m. and travels east to the at a rate of 60 km per hour. Car B leaves at 9 a.m. and travels north at 70 km per hour. How fast is the distance between the cars changing at 10 a.m.? At 10 a.m. we see that car A travels X distances at a rate of 60 kilometers per hour, while car B travels Y distance at a rate of 70 kilometers per hour, and both reach at the locations by 10 a.m. The distance at 10 a.m., which is represented by S, and the speed, which is ds over dt. Here we see the speed of car A, which is 60 km per hour, and car B, 70 km per hour. By using the Pythagoras theorem, x squared plus y squared equals to s squared. Implicity differentiation with respect to t, by using this formula, dx over dt plus 2y dy dt equals to 2s ds over dt. Car A needs 2 hours to reach 10 a.m. So here we have x, which is the distance, equals to 60 times 2, we get 120 kilometers. Meanwhile, car B needs 1 hour to reach 10 a.m. So y equals to 70 times 1, we get 70 kilometers per hour. We find s by using the same Pythagoras theorem. S squared equals to x squared plus y squared. S squared equals to 120 squared plus 70 squared, which is equivalent to 19,300 kilometers. S squared equals to 19,300 kilometers. The square from s we bring over to the other side, making it a square root, where s is now equals to the square root of 19,300, which equals to 138.92 kilometers. Sub the answer, which is the s, into, we get 2 bracket 120 close brackets 60 plus 2 brackets 70 equals to 2 brackets 138.92 brackets ds over dt, which is the speed between the distance of car A and car B at 10 a.m. At one side, we get 24,200 kilometers is equivalent to 277.84 times the speed between car A and car B. The speed between car A and car B is equals to 87.1 kilometers per hour. Thus, distance between the two cars A and B is changing at a rate of 87.1 kilometers per hour.